even though it was called something else by people at different points in history of humanity. So it's just that it's been uh, put to use a lot more often in the last 50 years compared to maybe the last 300 or 400 years where, and then even before there were some versions of it. So, and it's called Bayesian statistics or the Bayesian approach, but the term is not so important. The name Bayes actually comes from Reverend Bayes, who was actually a theologian, a priest in England, and he, those days people used to do multiple things in life, and so he also came up with Bayes' theorem, apart from the things that he was doing. I don't know what he did in religion, but I think this is his much greater contribution to all of us. Okay, so we'll just talk briefly about science, data, and models, and then we'll take it up from there. So, so the scientific method, just a very quick overview of that. So what do you think might be the first thing that we might want to do? Let's say that we are embarking on something. What's the first thing that we do if we are going to do some, let's say, a new piece of scientific research? Yeah? No, that comes later. Before that. Yeah?
Study about the thing we want to learn.
That will also come later. The first thing.
Plot a plan.
Huh?
Plot a plan.
A plot of what?
Plan. A plan of what you will do.
No, that also comes a little later. Yeah, any? No, that also comes later. No, that also comes later. No, all that will come. Yeah? Huh? No, that'll, yeah. It starts with a Q. Question, right? You will ask a question, right? Says questions can be very simple or complicated, right? How many bird species are found in the Ashoka campus? That's a question, right? Right? So, what's the relationship between the weather in Delhi and the crop burning in Punjab and Haryana? That's a scientific question, right? So the first thing that you ask is a question, and a question has been asked by people throughout the history of humanity. People have been asking questions and trying to find answers of one kind or the other, right? So that's the thing. The goal of science is nothing less than a complete description of the universe we live in, right? That's what we ultimately will do. And this is Stephen Hawking's quote. But fortunately, most of us deal with a very small and modest part of the universe. So while this might be the ultimate goal of science, we are dealing with a description of something which is a small part of that. It could be just a question about Ashoka campus. It could be something about Delhi. It could be something about some other village or whatever it is. Usually what we are interested in is a very small part of the universe. But this is like the ultimate overarching goal is to complete description. We are never going to get there, right? Because there are always lots of things left to be done. So science is a never-ending quest. Okay, and then you basically build theories and check theories, predictions, and so on. And another thing is that this is not about reality, because that might be difficult for us. There's no, sometimes you might say that we are trying to find out the truth, but actually it's much more about thinking about reality rather than actually reaching that reality, because there's a lot of things that we'll never know or it'll be difficult for us to find out. And so we shouldn't be thinking that we're going to actually complete something to its, know everything about some system. It might be really difficult. Always there'll be something left over for others to pursue. After we have finished our science, somebody else will take it up, right? So it's never-ending quest. So that's another thing to keep in mind, that you have to keep on building on previous knowledge and updating it. Yeah. So a scientific theory is a model of the universe or a restricted part of it. So when I say restricted part of it, it could be something about the Ashoka campus. It could be something about a lake It could be something about a particular tree. So a restricted part of it applies to anything that all of us are interested in studying. And a set of rules that relate quantities in the model to observations that we make. This is very important, right? So, for example, what geometrical or mathematical simplification can you make about the shape of the Earth? A sphere? It's not exactly a sphere, right? But for all practical purposes, when people were thinking about this hundreds of years ago, they said that a sphere is a reasonably good mathematical model of the shape of the Earth, right? Then after you have got a model for something, that model will not be as complex as the real stuff. Sometimes it might be a very simplified version of the real thing, right? So most of the models that we build, scientific models, statistical models, they are a simplification of something much more complex, right? But once you have built that model, we no longer think about the original thing that it's supposed to model, but about quantities in the model. So what are the quantities in a sphere? Radius, okay, you have diameter. So those are the quantities that then we will relate to observations that we make. So it's no longer the actual Earth now, but a simplified model of the Earth. And then we'll take the radius, diameter, perimeter, all of these things, surface area, all of this. Then people started relating these quantities to the observations that people were making when they were sailing around the world in a ship, or when they were looking at many things, phenomena over a period of time. They figured out that the observations that they were making could be related to the mathematical description of the right? So there will be other things also where you will have a mathematical or a statistical description of something very simple, like a linear model, that is relationship between one variable and another response variable. Let's say that on the x-axis you have the income of a household, and on the y-axis you have the percentage of their income that goes into food, right? So now think about this. You can have a very simplified linear relationship between the two, even though you know it is a much more complex thing. And yet, once you have come up with that simplified model, then we will take quantities in that model to observations that we will be collecting. So what are the quantities in a straight line relationship between x and y? What are the one or two things that you can think about? Any straight line. What? Points are, that's actually on the line, but the model itself, the entire thing, the entire line, what can you say about it? Will all lines be the same? No. So how do they differ? Huh? Yeah, that's fine. But I'm saying that what is it about a mathematical quantity about the line that you can then relate to real observations that you make on incomes and all of that. Slope, yes. So slope is a very important parameter that defines, and slope can be what? Can be positive, it can be negative, right? It can be very steep, it can be flat, it can be, right? So you also have something called an intercept that some of you might know, right? For a straight line. So anyway, so those are the quantities now. Once you have taken a complex phenomena and simplified in the form of a straight line or a regression equation, then it's the slope and intercept and quantities like that that we will be relating to the observations that we are going to make and the measurements that we make. We are no longer worried now about the real thing, because we don't know what the real thing is. We have a simplified version of it. Okay, so this is a scientific method. We all agreed that the first thing that you do is you ask a question, right? So each one of you can easily come up with a question of interest to you, something that you're curious about, and about the weather, about ecology, about people's incomes, anything, even about cricket or anything else. You could be asking any type of question that you are really interested and excited about. So once you ask that question, what is the next thing that you might want to do? So some of the things that you actually mentioned a little while ago, they'll all start coming in, but they'll come in a particular sequence. You have asked a question, yeah. Huh? Yes, you will do background research. So that's more or less correct. You will find out what is already known about that question, right? So people may have done lots about that question. And if they've done so much, you might want to say, okay, do I really need to ask this question? Because it seems to have been answered pretty well by lots of people, right? So you might want to change your question a little bit, make it a little bit new, because one of the goals of science is to update knowledge, right? So you don't want to repeat something that has already been done before. So you might want to change it a little bit, right? So that's why it's so important to find out what is known about that question, right? So let's say that somebody asked a question, how many species of birds are there on Ashoka campus? So it's not as if we don't know that. There are all the ecologists, colleagues of ours who are teaching you, they will tell you that there are ways of finding out from the internet and from experts and from even people who are part of the Ashoka faculty who are interested in birds, that they might have made a checklist. The people upload it on something called eBird, right? So eBird is a portal where every birder who sees a bird in a particular place, she or he will say that this species was seen in such and such place, such and such date, and then I'm sure that there is an eBird list for Ashoka campus. Is there? Good. See, there is a eBird list. So you're going to assemble all previous information and evaluate the relevant data and information, right? But no matter what they have done, doesn't mean that they have answered that question. They might have done a couple of seasons of bird watching and come up with a list of 30 species of birds or 35 species of birds or whatever. You might find that actually there is a opportunity for you to fill the gap and really complete all the seasons, bring in winter season when migratory birds will be whatever. Some gap you might see in the previous work, and then you might want to add to it, right? So you do see that it's not repetitive. Actually, I think this is a relevant question to ask because it's not been answered completely. Or for that matter, how many species of bats are on campus, right? I think some of you have been going around with Rohit trying to figure that out. So, for example, Bangalore has between 12 to 15 species of bats. I don't know about Delhi or NCR, but I'm sure we can get there sometime. Okay, so then based on all previous information, you'll evaluate the relevant data. You'll find out whether the question you've asked is novel enough. Novel means that it's going to add some new knowledge to the world of science. And so if you think it is going to add value, then you don't have to change your question, or you don't have to drop your question, right? So sometimes it happens that people have done so much work on that question that you might want to change your question, but anyway, so then based on this, you will design an experiment or an observational study to address the question. You will consider costs and benefits. So it's very important for us to consider costs and benefits of a study, because you need instruments, you need people's time, you need resources, and all of that to do that. So you have to consider all of that when you're designing your study. You will carry out a study, and you will use whatever data or evidence that you have to update knowledge. So this is the important thing, that we are always wanting to update knowledge. So previous knowledge exists, and you're just going to add to that, right? In some cases, previous knowledge may not exist, in which case you're the pioneer, but in most things that we do, there's always somebody who's done something interesting to which you're going to add stuff. Okay, then you will draw some conclusions. If tentative, you can repeat the steps 3 to 5 if necessary, because if you want some course correction, your measurements were not okay, your instrument was not okay, you think the method needs to be changed a little bit, all of that you can do. I'm sure you can do that when you're studying bats or birds or whatever else you want to do. Then you will make a scientific inference. That is, whatever question you asked, you will be able to start beginning to answer that, right? So you will make a scientific inference. And remember that even though this is a class about statistics, we are not saying that you're going to make a statistical inference, because in the way that we want all of you to do, integrate statistics and science, there is no such thing as scientific inference separate and statistical inference separate. The two are integrated and done together. So that is one thing which is a departure from the way it used to be done in some places, where science was done first and then the statistics was supposed to be some sort of an afterthought, that you come back after a study and then say, okay, now I want to analyze my data and figure out things. That is the old school. And so here in the newer approaches, right from the beginning, science and statistics are together. So that's one thing that, or maths for that matter, statistics is an extension of mathematics. Okay, and then you will make predictions with uncertainty. Why? Because one of the goals of science is to predict the future or to predict a future observation, right? So you asked a question, how many species of birds are there on Ashoka campus? And based on the uncertainty or whatever it is, you might say that actually my prediction is that there are so many species of birds, right? You may have recorded only 35 species, but you have evidence together based on everything else you have done. You might say that my prediction of the number of bird species on Ashoka campus is about 42 or 43. With some interval you can give. Uncertainty is important. Remember that you won't give you one answer, you're going to give a range. So that's another thing. The one thing which is certain about this approach to the scientific method is uncertainty. Okay, that's the only thing which is certain. So you'll always need to quantify the uncertainty. Anyway, so the uncertainty in science can come from various things, right? It can come from previous information. There could be things which are, incorrectly done. People might not have observed properly, or they may not have had the means to study something properly. So there will be some uncertainty coming through that, and it will creep into your work also because you are building on that previous work. It can come from the type of model you've constructed. Like a sphere might be a reasonably good model of the shape of the Earth, but the model that you have chosen for your particular phenomena might be inadequate. Maybe you left out a couple of things in your description of the model. Your assumptions might be wrong about certain things. All of that, right? So, for example, you might assume that the birds in Ashoka campus don't interact with some particular another campus which is maybe 2 kilometers away. And if you make that assumption, you might actually underestimate the number of bird species on Ashoka campus, because actually Ashoka campus is part of a larger set of habitats that links all the, so things like that. Anyway, and then there is also measurement error and sampling. Your instrument might not work properly. You might misidentify a bird species. These are all examples of measurement error, and your sample size might be too small. You have gone out only 3 times on the Ashoka campus to look at birds. If you went there 10 times, then you would have a greater chance of covering all the bird species and so on. Or you went at the wrong time of the day. These are all things that birds are active in the morning and later in the evening. So. And bats, you can't sample for them during the day, right? You would have learned that. So, how many of you have been going around looking for bats? Oh, good. Okay. The other thing is that the same data can lead to conclusions depending on other available information. And this is what we are going to be discussing today. That the data is the one that all of us can agree on. But the conclusions that we draw with that data may differ depending on other information that you and I may differ on using. So that is one thing. So coming to the shape of the Earth, we said, right? So a long time back, people didn't know what the shape of the Earth was. So they were wondering what the shape of the Earth was. Right? And what were the 2 competing ideas about the shape of the Earth? One was that the Earth was flat, and the other one was that it was round, right? Okay. Then people started making observations. People by then had built sailing ships. They built harbors and ports and going around. So now, if you were in a harbor or a port, and there was a sailing ship approaching the harbor. Now consider the Earth as a flat and Earth as round. Okay? Now, if the Earth was flat, what would you see when a sailing ship is approaching the, remember I'm talking about hundreds or maybe even 1,000 years ago, when there were sailors or people on the port watching a ship approaching, a sailing ship with a mast and sails and all of that. So it's approaching the harbor. So what will, if the Earth were flat, how would you see the ship? And if the Earth were round, how would you see?
If the Earth were flat, we would have been able to see it from like very far because it was flat. And if it was round, we would have seen it coming like this and then finally see it.
Okay, you're getting there.
When it's flat, we see the height of the mast, but when it's round curve, we see only the mast.
Oh, exactly. So so here are two competing ideas of the shape of the Earth, or two models of the Earth, and the observation is common. Okay? Now, some of the sailors might be drunken and all that, they might imagine things, but let's say that it was a good observer, and she or he saw only the sails being visible first, the mast being visible first, and then after a while, when the ship comes a little closer, you can see the rest of the ship, right? So that is consistent with the model of the Earth being round, right? But if it was flat, the entire ship would have been visible together. So now you have one observation you have made, and it's consistent with one of the models of the Earth and not with the other, right? So this is just one, okay? Then it took other phenomena to be observed before people were convinced about the shape of the Earth. What other cosmic or other phenomena that you can think of which would tell us about the shape of the Earth that people in ancient times started observing? Yeah?
How the sun rises and sets?
That is not exactly, that's to do with something else. But now I'm talking about just the shape of the Earth that is clearly visible. Yeah? Eclipse, did you say? So there are, yes, the position of the star, that's a little complicated. Yes, people did do that. But eclipse, so in an eclipse you can actually see, right, the shadow. And so that also told people that yes, that this observation I'm making, my second observation, is also consistent with this model of the Earth being a curved round whatever object, right? So this is how so the consistency of data with a particular model, okay, that's called likelihood. Okay, that is how probable is an observation of the sails, a mast being visible first, and then the entire ship. How consistent is that, or how probable is that observation if I assume that the Earth was a curved round object? And the probability is very high. Whereas the likelihood that you will be able to see the sail first and then the rest of the ship later is not consistent with the shape of the Earth being flat, right? So the likelihood is low. So this is that is the consistency of data as when you assume a particular model. This principle is called likelihood, and then you will later on, and when you study further, you will hear about maximum likelihood and all, but it's the same principle. As long as so anything that we do, we completely be relied upon, and each one of us will have a slightly different way of assessing this information. Plus, I may not read the reviews that you have read about that restaurant. I may not have a friend who has gone there and said the food is fabulous. My probability for the food being good in that restaurant after reading the reviews might not be as high as yours because you've had a friend tell you that she has eaten there and it's very good food or whatever it is, right? So this prior information that's available to each one of us when we are updating probabilities can differ. Yeah. Okay? Okay, so now, there are two events A and B. I tell you that event B has happened, okay? So event B has happened. So this is something going back to our high school All of you have done Venn diagrams? Yeah? Okay, those of you who haven't, just bear with me. Okay, when we say an event has happened, that means it's like saying rain has happened, or this bird has been seen, or this bird sat on the. These are all events. Okay, so there are two events A and B, and I tell you that the event B has happened. What is your probability for event A? Event A is not even shown on this picture. Okay, if event B has happened, what do I need to find out? What else do I need in order to talk about event? If B has happened and I want to find out about A, what do I need to know about A? Yes, that is what is the intersection between A and B. So this is known as shared sample space. So if B has happened, the only way we can say something about A is if we know what is common between events A and B, right? So for example, event B might be that rain has happened, and event A might be that a dust storm will follow, or whatever it is. So things like that, anything like that. So now the probability for event A, okay, the chance of event A happening, given that you know that event B has happened, depends on. So when we say A conditional on B, that's the meaning that B has already happened and now we want to predict A. And that you can only predict if you know the probability of that common space. That is where both events are happening together. If you know that part, then you can, knowing that B has happened, you can predict what is the probability for A, right? So just like that, this weather report, the weather report said this, and then something else, so you're basically updating probability. So B has happened, now you want to predict A, and for that you need to know the joint probability of A and B, right? So in the case of the weather report, what would that mean? It would mean how often the weather report and actual rain have coincided. That would be the intersection. That would be the example. And then you will have to divide it by the probability of B, because B has happened. B is the starting point. Okay? And then this is what is going to tell you about whether A can also happen. So this is something, this is called conditional probability. And you will, if those of you who haven't done it, you will learn about it, but it's very similar to what we just did with the weather report and so on. Now, I'll change it. I'll say that event A has happened. Okay? Now you want to say something about event B. Now what is there, do you see? The probability of B given A is the probability of B intersection A. Now what is the difference between A intersection B and B intersection A? Any difference? No, but I'm just saying, if I write A intersection B or B intersection A, is there any difference mathematically? No, right? Now keep that in mind, write it down, because now there are two ways of writing the numerator. There are two ways of writing the numerator. So now B conditional on A will have probability of B intersection A divided by the probability of A, because A happened first. Okay? A happened, and then you're trying to predict about B. So this is just another way of doing the same thing, but except that this time A has happened first. Earlier, B happened first. And now we have all agreed that earlier we had probability of A intersection B, and now we have B intersection A, and mathematically they're the same. So if the numerator is the same, that means there are two ways in which I can write the numerator. Because if I take this here and multiply this here, and then if you go to your the previous slide, you can rewrite the numerator in two different ways. Has somebody written that down or figured it out? Remember this, that if we take this here, then you can write P A intersection B in one way. And now I can write this in another way, right? So if the numerator is the same, that means the product, those two different ways of writing that are also the left hand side is equal to the right hand side, left hand side is equal to right hand side, right? So that gives us a very important result. So if B is independent of A, that means regardless of whether A happens or not, it doesn't matter to B, then you're going to get the same probability for B regardless of whether A has happened or not. But the probability of A intersection B is when both of them are occurring together. And that's a product of two probabilities. And remember, probabilities go from 0 to 1. So probability of A will be 0 to 1, probability of B will be 0 to 1. So if you take two events, like it's going to rain and there's going to be thunder, there's going to be lightning. The probability of rain and lightning is always going to be lower than the probability of either rain or lightning alone. Anyway, you won't get lightning without rain, but I'm just saying that if you had to look at a joint probability of two events, it will always be lower. That's another thing. Why? Because probabilities go from 0 to 1. If you're taking the product of two probabilities, the joint phenomena's chances of happening, that is rain with lightning, is always going to be less than the probability of just rain. Okay? Anyway, so now we know that A intersection B is equal to B intersection A. Therefore, you can rewrite the numerator in two different ways. So this is a very important and simple thing that's basically which I think that by the time you do Venn diagrams and do this intersections and all, you should be able to. So basically, you're almost there in terms of understanding Bayesian statistics. So there are two different ways. Now that we have agreed that this is and this are the same, therefore you can rewrite. So this is very powerful. That A. So what is this? The probability of B occurring multiplied by the probability of A conditional on B, and this is the probability of A occurring multiplied by the probability of B conditional on A. So these probabilities here, this PA and PB, they are called prior probabilities. Okay? And this part here, the probability of A conditional on B or B conditional on A, this is like the likelihood part. That is conditional on something. What is the probability of that happening? So that's okay. So you folks have been doing this, right? Rohit has been going around with some of you. Yeah, all of you know Rohit, right? Yeah. So, so you have been searching for a species of bat on Ashoka University campus, let's say. So what are the bats which are found on Ashoka University? One example. Which bat?
Greater yellow house bat.
Okay, okay. What any other bat? Pipis, huh? Pygmy pipistrelle bat. Okay, so let's assume that, yeah, you wanted to say? Tomb bat. Ah, good, yeah. These people are good. So all of you have been doing this, and you probably used, these are all insectivorous bats, and you all know that every insectivorous bat has uses a particular frequency called, there's a phenomena called echolocation, right? So they send these signals, that signal will hit some insect, like a mosquito or a fly, right? And then it will come back, and the bat will be able to navigate, will be able to estimate how far the insect is, which direction it needs to fly. It will go and capture that insect, right? Bats also use this for navigating around the place. So they use this echolocation, and each insectivorous bat has a particular frequency or wavelength at which this echolocation is there. So Rohit must have used a device like this, right? What is the name of the instrument you used, Rohit? Bat detector, right? It was a bat detector. So it can detect the signals that are coming from the bats, right? Is the bat detector 100% reliable? Right? So you may find a situation where the tomb bat is there or the pipistrelle is there, but the bat detector did not, so it's a detection issue. Remember, COVID also, the tests are not 100%, right? So there is something called detection probability, okay? So now bear with me that there's a species of bat and you are interested in finding out something about it on the Ashoka campus. You have a bat detector because you can't always see the bat. You have to use some measuring device like this. And then there are 3 patches. Ashoka University has got 3 patches, okay? And based on previous work, Rohit tells us that the probability of the tomb bat being in patch 1 is 0.7, patch 2 is 0.2, and patch 3 is 0.1. Okay? Everybody got it? 3 patches on Ashoka University, and the tomb bat prefers patch 1 much more, it's seen much more there, it's found there, and then with less probability. And then remember that the bat is definitely found on Ashoka campus as a whole across these 3 patches. So these probabilities 0.7, 0.2, 0.1 add up to 1. What does it mean? It means that across these patches the bat is definitely there. Okay? So this is based on previous information. This is known as a prior probability of the bat being found in patch 1, patch 2, patch 3. Then what do you folks did last evening? So then the other thing is that you also have a bat detector with you. Now the bat detector, Rohit tells us that probability of detecting a bird or animal, in this case the bat is an animal, is 0.65. That is, if the bat is there, if the tomb bat is there in patch 1 or patch 2 or patch 3, if it's really there, flying there, your bat detector has a probability of detecting it 65% out of 100, which means that it has a probability of not detecting it if the bat is there of 1 minus 0.65, which is 0.35. Okay? Now you know what is the information available to us so far. We have this prior probabilities of the tomb bat being there in patch 1, patch 2, patch 3. And then we also know about the reliability of the instrument. So this is the 2 pieces of information we have right now. So our probability of the bat being found is still 0.7 in patch 1, patch 2 0.2 and 0.1 because we haven't collected any data. Okay? Then last evening you guys you search in patch 1. You went with the bat detector in patch 1 and you do not find the bat based on you didn't see the bat and you didn't, didn't record, your bat detector didn't record it. Okay? Does it mean that the bat is not there? What does it mean? It could be there, it couldn't be there, right? Because your instrument is not 100% correct, right? So this is the data you have. You went to patch 1, you switched on the bat detector, you went around and you did not detect the bat. Okay? Now, how will you use the pieces of information that we have got so far? That is the prior probability of the bat being found in each of the 3 patches and the fact that you went to patch 1 and you did not detect the bat. How will you now change the probabilities of the bat being found in each of the 3 patches? Okay? Any ideas how you will do that? Very simple. So the animal or bird may still be there, but now it is less likely, right? Would you say that the fact that the bat detector did not detect a bat, would you reduce the probability of the bat being in patch 1 by some amount? Right? Because it's reliable 65%, right? The detector. So you didn't detect the bat using the instrument. So remember, probability is a state of beliefs about some phenomena. Would you update your probability for the other 2 patches based on this? Would you think some readjustment is now required? Because earlier it was 0.7, 0.2, 0.1. Yeah. No, that we haven't done. This is the only piece of information we have. Yeah. So what would happen? So you intuitively just think that I did not detect the bat. It's a fairly reliable instrument. So in my mind, would I reduce the probability of the bat being in patch 1 and increase the probability of the bat being found in patch 2 and 3? Right? Now, how do we do this? Now, let us calculate the updated posterior probability with the new evidence that we did not cite the animal or bird in patch 1. So, that's the only piece of data you have, new data that you have. Earlier, you just knew about the prior probability of the bat being found in patch 1, patch 2, patch 3. Now you know that you went around with Rohit and you didn't find the bat in patch 1. Now you want to update the probabilities. Okay, so the probability of the bird or animal being there and you not being able to find it is 0.7 into 0.35, 0.245. The two probabilities, the prior probability of the bat being there in patch 1 and the fact that you did not detect it, which is 1 minus 0.65, which is 0.35, so you multiply the two. Now this is the updated piece of information you have. Okay, so now let's update our original table. Patch 1 now has become 0.245. Why? Because now we didn't detect the bat. But you add these three, do they add up to 1? Can somebody tell me whether they add up to 1? No, and we know that they should add up to 1. So what do you have to do? You have to divide each one by the new sum, okay, to normalize it. Okay, when you do that, now you will get posterior probabilities for the bat being found in patch 1, patch 2, patch 3. So what has happened because of the new data and evidence that you collected with the bat detector, that too with non-detection, remember it didn't detect the bat, you reduce the probability for the bat being in 0.45 and the other ones have gone up a little bit. Okay, in terms of going back, where should you invest your next effort? Would you go to patch 2 or patch 3 or which patch would you again go back to invest time in? Say it loudly. Patch 1, because it's still higher than the other two. In spite of the fact that you did not detect the bat there, because of the high prior probability of the bat being there, prior knowledge is so important, and in spite of not being detected there, you still need to go back there. You still have the better chance of finding the bat in that patch. Okay? So this is how you will build on information and knowledge and update your probabilities. And so it's not as if that Rohit and company should immediately switch to the other two patches. No, they should invest more time in looking for the tomb bat in patch 1 and then go to the other patches. Okay? You can also use this as a way of saying that I have so many volunteers, I have so many hours of observation, I am going to put them in proportion to these probabilities. You could do that. You could send 45% of your resources into patch 1, 37 into patch 2 and remaining 0.18 into patch 3. So this is another way of acting on information. You can design your study as new information comes in, right? So is everybody clear about this example, right? About measurements or a detector device which is not foolproof. Most of the instruments that we use, observations that we make will always have some uncertainty associated with it, right? And so we have to make use of this, and this whole issue of detection is very important in ecology and wildlife biology, because most of the time the animals and birds are elusive. We do not see them. That doesn't mean they're not there. It just means that our ability to detect them even when they're there is somewhere between 0 and 1. It's not 1, right? And how did Rohit come up with that 0.65 probability of the bat detector detecting the bat when it's actually there? On previous occasions, you might actually see the bat flying and your detector is also. So you will have that. Those are precious observations. So over a period of time, he compiled all of them. He's been doing this for years actually. And I got the number from him just a little while ago. That's what I put in there. And then that 0.65 has come from previous observations where he was able to use the bat detector and see the bat independently, and then he figured out that 65% of the out of 100 it's able to detect the bat if it's there. Okay, so and that requires a lot of so you will not always find somebody as reliable as Rohit and so on. You might have less reliable information, and in which case your results might be slightly different. Okay, so now we talked about A and B. Now we'll just extend this idea to slightly different. Instead of A and B and all of that, we have H1, H2, H3. Somebody a little while ago in the beginning, somebody said about what do we do in science. You mentioned some word starting with H. Hypothesis, right? So consider H1, H2 and H3 as three competing hypotheses, okay? Or three ideas about how a particular natural phenomena works, okay? Now, can you see that all H1, H2 and H3 are all enclosed in this box? What is that box? It's a box which contains all potential observations, all possibilities. I have basically said that other than H1, H2, H3, there are no other way of explaining that phenomenon. So these are known as mutually exclusive hypotheses or ideas, like the earth being round or flat. They don't share sample space. You can't have the earth being flat and being round and sharing any sample space, right? They're mutually, so can you see that H1, H2 and H3 do not share any boundaries? Yeah? The boundaries are here, boundaries are there. But what is sharing boundaries with H1, H2 and H3? It's data. Data is the only real stuff, right? So this time I have collected the data. My data is sharing, with which of the hypotheses is my data sharing the most space? H3. Okay, tomorrow tomorrow or day after, I go out and collect data again. You think I will get the same overlap with H1, H2, H3? No, because my data is going to be different. So this oval is going to shift here or here or here or whatever it is, right? So that's one thing to be clear, that the only thing real is data, and it can share space with competing ideas or hypotheses, right? And depending on the that's why it's so important to collect a good piece of data, because you want to make sure that measurement errors and other things are minimized, your sample size is good enough, so that it can actually have the greatest overlap with probably the mechanism that best explains. So that is the idea of how data can share space with hypothesis. And the same thing that we did with Venn diagrams, with A and B, you can do with data and hypothesis. You just replace A and B with H1, H2, H3 and data, and you've got your Bayesian statistics covered completely. So if you understood what we did with A and B, you're done. You're all experts in Bayesian statistics. How much time do we have? We have, okay. You guys want a break, yeah? Yes, you can see that there's no overlap. There's overlap between data in each one of them, but here the boundaries are, right? Okay, so now, yeah, what we ultimately want is the probability of the hypothesis. Okay? What we probably want is what we want ultimately in statistical and scientific inference is the probability of the hypothesis. So now you did that thing with A and B. Whatever you did with A and B, can you please repeat it with H1 and data? What does it mean? It means what is the probability of hypothesis H1 conditional on the data having been collected? What is the probability of hypothesis 2 conditional on the data that you have collected? And the same thing for, right? So now you've got your same Venn diagrams and the same intersections, but instead of A and B, you now have H1, H2, H3 and data. That's all. Mathematically, there's nothing different. It's just adding a little bit more complexity in. So you can derive this from yourself actually. So what you want is the probability of H1 conditional on the data. Remember that you had A and B there, now you have probability of H1 intersection D. That is the shared sample space between of hypothesis 1 and the data that you have collected. So that's the numerator now. And it is conditional on the data being collected. That's all. So if you are able to derive that A and B and the intersection and the conditional probability, which you can actually, if you go back, you will be able to derive this. You don't have to mug this up. You don't have to. You can each time, whenever you are in doubt, it will take a few minutes of your time to come up with Bayes' theorem on your own. You don't have to really know. Anyway, so I'm just saying that now this numerator is the joint probability of hypothesis H1 and the data, right? So this intersection, as you know, remember you go back to the two ways of writing the numerator. You can write it as a probability of the data conditional on the hypothesis multiplied by the prior probability of the hypothesis. And this part, the probability of the data conditional on a hypothesis or a model, this is called likelihood. This is part of it is called likelihood. So now you have replaced the A's and B's as events with data and hypothesis. That's all. Otherwise, everything is the same. So if you were able to derive that and understand that part, this part is. So this is basically your Bayes theorem. The prior probability of H1. In the case of the bats and Rohit, what is the prior probability of finding the bats in patch 1? What was it? Do you remember? 70%. Huh? No, the first, what is the? You guys are 0.7. So this is the prior probability of finding the bat in patch 1, right? So that's like an example of a prior. Okay. So you did all that and now you have this part. So all of this, I'm not going to get into this. I want you to just appreciate this part, that the probability of the data, assuming hypothesis 1 is true, multiplied by the prior probability of hypothesis 1, divided by the total probability of the data is basically what you really want to get at. And your frequentist statistics, the difference between the conventional statistics and Bayesian statistics is that in Bayesian statistics you can actually update probabilities with your data, right? Whereas in the conventional statistics, prior information plays no role. You do a nice literature review saying, you know, this guy said that, she said that, and this is what they found. You'll write that beautifully. But quantitatively, it's not going to enter into any calculation or anything. So the difference between the Bayesian way of doing statistics and the non-Bayesian way is that the prior information is quantified and enters into your estimates of updated probabilities. So that is the big difference between the two. So anyway, I'm just going to now give you a nice practical example, which all of us will be able to get. So suppose there are, okay, yeah. So all of you have played Ludo, Snakes and Ladders and things like that, right? Yeah. So now all of you know dice. Now let's say there are 3 kinds of dice, okay, manufactured by different companies. So each company's manufacturing process has its own strengths, weaknesses, and the dice from each company is unique in its behavior and own probability distribution, right? So there are 50 dice from company 1, 25 from the other 2 companies. And the shopkeeper, what he does or she does is mixing up all of them in one bag. So how many dice are there in total? 100, out of which 50 belong to company 1 and 25 each to the other 2 companies, okay? Now this is the mathematical description of the behavior of each of the dice. Company 1, company 2, company 3. Pay close attention. This is your conventional dice where it has got equal probability for each outcome, right? Got it? Equal chance of all of them, right? Look at the other 2. Do they have equal chance? But you add up across this, Add up across all of this, what will you get? 1. Add up across all this, what will you get? And do it and then tell me. I can also make a mistake, but I want you to actually just add it up. Okay, it should add to 1 because across all the outcomes, the probability has to be 1. Okay, what about model 3? Adds up to 1? Yeah? Across all this, if you add up all of these, yeah? Now, what is peculiar about model 3? Okay, 6 has no chance of coming up, right? Now, let us generate some data. Suppose I roll the dice. Okay, suppose I get a 1. Suppose I get 1 when I roll the dice. Can you say that it came from model 1, 2 or 3? It could have come from any one. You can also compute what's the probability of getting a 1 in dice in model 1. It will be, what is the probability of getting a 1 conditional on model 1 being true? It would be 1 by 6. It would be 1 by 6 for this one, but it would be 1 by 5 for this, right? Now suppose I keep rolling the dice. I get a 1, 3 and a 6. Which model can I knock out now out of the reckoning? I got a 6. So, because model 3 has 0 chance of getting a 6, that means my data, I'm lucky enough to get a data where I have knocked out 1 out of the 3. Now it's only between models 1 and 2. But you're not always going to be lucky. So what it means is that you must collect more data. The more data you collect, the greater the chances that you will actually get a 6. If you get a 6, you can knock out. So that's how you see how consistent the data is with the models. And so that's why you can do this experiment. You can note this down. I'm going to leave these slides with you. I would ask you to roll the dice or generate it on a phone or whatever it is. And then you can find out the probability of getting observations 1, 3 and 5. Okay, what is another assumption about the rolling of the dice that we are making here? Suppose we repeatedly roll the dice. The second time I roll a dice, does it have anything to do with the first time I rolled the dice? Right? So you're all agreeing that whatever I get on the second roll has nothing to do with what I got, right? So it is called independence. So they are independent of each other, right? So when events are independent of each other, the probabilities can be multiplied, right? You remember that we showed you that other example earlier, where you can remember we said that the probability of rain and lightning, right? So think like that. So when you're talking about the joint probability of getting a 1, 3 and a 6, you will multiply those probabilities. So let's take the joint probability of getting a 1, 3 and 6 for model 1. What would it be? 1 by 6 multiplied by 1 by 6 multiplied by 1 by 6. 1, 3 and 6 for model 3 will be 0. Because you'll be multiplying it with a 0 probability. So right? So, and then you will get some for model 2 as well. So this is known as likelihood. How probable is the data conditional on model 1? How probable is this observation conditional on model 2 and model 3? Right? The more data you collect, the greater the chances of being able to differentiate between. So what was the prior probability? If you picked a dice at random from that bag, what is the probability that it belonged to company 1? 50. So 0.5 was the prior probability that it belonged to company 1, and 0.25 for company 2, 0.25 for company 3. Now after you've rolled the dice and you got a 6, you eliminated model company 3. Right? So what have you done? You have updated your probabilities. You have updated your probabilities of that dice belonging to company 1, company 2, company 3 by collecting data. So the data is the new evidence that you've added, and now it's no longer 0.5, 0.25, 0.25. It's going to be 0 for model 1, model 3, and it's going to be something else for the other 2. Right? So I would urge you to use this, roll a dice a few times, and compute the probability of getting your observed data conditional on model 1, model 2 or model 3. Yeah. Yeah, I think we should, 40 minutes, so I should, let me see. Yes, yes. So I think that I've done quite a bit. There are a few things that I can do more, but I would rather now have. Maybe you can conclude the. Yeah, so I just want to say that I just want to show you one example that when you're talking about prior on model parameters, suppose you have a lake. Do you have a pond on Ashoka campus? Any type of pond? No, no. Swimming pool? No, this is not a swimming pool. No. Okay, let's assume that there was a pond on Ashoka campus. Okay, and it rains, and is there a rain gauge on campus? Weather station? No, I think they should invest in one. Maybe they have.
They could, but I don't think we have enough rain for that.
Enough what?
I don't think we have enough rain for that.
Enough rain, it will not these days, yeah, but it will rain in Delhi at some point in time. Come on. Yeah, yeah.
Show your video to the founders.
So what I'm trying to say is that suppose I say that I'm going to measure the amount of rain that falls in every hour, and I measure the level in the pond. Okay, what sort of relationship will you expect just based on common sense? If it as the higher the amount of rain in each hour, do you expect the level to go up in the pond or go down? Go up, right? So the relationship between rain and whatever pond level or stream flow or whatever it is, you expect it to be a positive relationship, right? But you don't know how steep it is. That's the only thing you don't know, but you know it's going to be positive. So I can, as a prior information, as a statistician, I'm not going to get into how do we do it is, you can say that my slope is going to be positive. You know that from already. Then you collect some data, and then what will happen? You can assume that a very weak slope but positive in the beginning, and you will collect data with rainfall and pond level. What will happen to that slope? It will shift from your prior either up or down, and that is building on. So that's how we can use any mathematical description of nature and use data to update the how it actually looks finally, right? And with more and more data, this line might shift steeper or it might become a little flatter depending on where you started off with, and that is basically building on existing information and knowledge. Now, in the Bayesian approach, we can actually start with a priori model, prior probability and prior parameter value of a positive slope for this relationship between rainfall and pond level or stream level. In the conventional statistics, you know what you are assuming? That there is no relationship at all. So you can't quantify the prior information in any way. So they will use that in literature review, that people have observed, that hydrologists have observed that as rain falls, pond levels may go up. But in the actual regression equation, when you fit that statistical model, the null model is that it's a flat line. Okay? So that is known as a nonsensical null hypothesis. So the Bayesian approach allows you not to have a nonsensical null model, it allows you to have a plausible null model which is based on prior knowledge and information which is sometimes common sense. Okay? So another example, suppose I go to some forest and I completely clear all the trees in that forest, and somebody has some information on the number of bird species which was found before and after. Okay? If you were a Bayesian, you would know that from previous knowledge that the number of bird species is going to reduce. Oops. Not going any, okay, wait. I think I've removed that line, but basically I had a slide where there was a hydrology model which tells you that as rain falls, what happens to it. How much of it goes into the soil, how much of it flows on the ground, how much of it. So that is a mechanistic description of a hydrologic model. That will tell me that as rainfall increases, the level of the water in the pond should go up based on a mechanism. So that mechanism should be, you should know that based on previous knowledge and all, and then you will prevent the problems of correlation and causation being confused. So just because pond level goes up with rainfall, unless you actually knew about why it's happening, then that is a starting point for even trying to fit a regression equation. Otherwise, you can fit a straight line. You might find that two variables are giving a straight line that actually both of them might be driven by a third variable which you haven't measured or know about. And these two are actually not really related to each other. Yes. So it's very important that you have as we said, right, the first thing you do is build a model of how nature works. So you build a model, it could be a conceptual diagram, it could be a mathematical description, it could be a statistical description. That is what will tell you, okay, that this is the response variable, the pond level. And my driving variable, that the one that makes the pond level go up or go down is going to be the amount of rainfall or whatever it is. So you need to start with the model. Yeah. 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 Yeah.
You said that the guy worked out the Bayesian,
Yeah.
Concepts and found the gold.
Yes.
But he was arrested later.
Yes.
But then, was this used for any other study? Whatever he found out, was it published or what happened really?
It's been written about by statisticians, and they probably have peer-reviewed papers also about how the Bayesian method was used for that. The guy was very smart. He was an entrepreneur, and he knew that this Bayesian approach is the one that's going to really get him the. But the only thing is that he didn't share the loot with the people who contributed to it, and so he just disappeared for 20 or plus years, and then he was arrested much later. And so it's a fascinating story, and there are many such things, many such phenomena which have been discovered, or either the location of a place or some important piece of information that gets updated simply because people used a Bayesian method. And this is of course the most celebrated example because a lot of gold and everybody's excited about gold and loot and crime and stuff like that. But of course nobody was killed. So that's a good story in that way. He did fool a lot of people, but ultimately, I mean, the fact that the shipwreck was actually located and the gold was retrieved by this group is really a fascinating story. Yeah. Yeah.
Chandigarh. Can you hear me?
Yeah, yeah.
Hello, sir. I'm Anamika. I'm from Chandigarh.
Yeah.
I had two doubts.
Yeah.
You talked about a plausible null model in the Bayesian theorem. What does it depend on? What factors?
It depends on prior knowledge and information. So, for example, if you suppose you say that people with higher incomes have a greater chance or are going to spend more on their children's education, right? So household income versus money spent on education of children. You might say that there is a positive, I think there is a positive relationship. It's based on prior knowledge, prior information about how society functions and how people behave or respond. So instead of saying that I don't know anything about this and that there's no relationship between the amount spent on children's education and socioeconomic status or income, that's probably not a good starting point, which is what your conventional statistics would. It would have a flat line between these two variables. Whereas in the Bayesian one, I would have a positive slope. That much I know, it's going to be positive. How steep or how flat it's going to be, I'll correct some data, update my prior beliefs and do that. But at least I'm not starting off on a nonsensical base.
All right, thank you. The second one, basing off of her question.
Yeah.
Do you know of any other morally ambiguous math criminals that we can read about?
Mass criminals?
Math criminals.
Math
People who've
criminals.
used math.
Oh, I'll have to look that up. It'll be a good story, but a lot of interesting things have been done using Bayesian approaches, and this is just the most notorious or most famous of them, because there's a lot of gold. I mean, I think they said $20 million. I know it's a huge amount of gold actually. I think most of the things were gone by, I don't think the experts and others really got much out of it even after the guy was arrested. Because anyway, I think gold which is found, I don't know what the laws are, I don't think you're supposed to just take it just distribute it amongst your friends or whatever it is. So there must be some rules somewhere. Yeah. But I hope that you got the gist of it, right? That we are Bayesians in some ways, right? We talked about the restaurant example, where you want to find out, you want to go decide whether to go to a restaurant, and you want to at least have some probability in your mind between 0 and 1 of the food being good there. And I said that you will look at reviews, but then reviews are manipulated. But then you've got a good friend who's eaten there, whose culinary tastes you really respect. So when she says that this food there is good, then your probability has gone up, right? But if there's another friend who told you whose taste in food you think is bad, and he told you that the food there is good, then you might not change your probability, or you might even lower it actually, right? So depending on the reliability of the source, you can update your probabilities. Yeah.
Good afternoon, sir. I am Earth Singhal from New Delhi. So these days we have observed a lot of human bias errors in AI models and their data. So do the ecological studies or statistics account for the human bias, human errors while collecting the data, and how do we solve them? Or have we seen some cases where the studies have been impacted by the human bias?
Of course, I mean, human bias is definitely going to be there. I mean, the thing with bias is that it can come from a faulty methodology or whatever it is, there are things like measurement error and things like that. See, inference is a separate thing. That is, after you've finished collected all your data and you've updated your posterior probabilities and your probability of the hypothesis model, you can make an inference, right? So whether a person should be biased or not, that's a different thing. But you mentioned about AI, right? I'll tell you an example of how we'll really all have to, because AI now can tell you what code to write for doing Bayesian analysis. And actually it's pretty good. It actually says these are the things you have to do and all that. But there are some things where it has still not. So the other day, I gave the name of my 2 dogs and my cat, and asked the ChatGPT to make up a poem. And we mentioned one thing about each of the pets, that this one is naughty, that one is this and all. That's all. And it made a very nice poem which rhymed and so on. But what it did is, it made the cat run away with the shoe. Cats usually don't run away with shoes, dogs do, right? So there was some piece of information that it was not able to get from us or from so it should have known about prior probabilities of cats and dogs, how they like to play. Cats generally like to play with smaller objects and other things and all. I don't think I've come across any cat which likes to run away with a shoe. So I would say that the prior information that the AI model used was inadequate. It should have known from the wider literature that dogs love to chew and run away with shoes. And in that poem, which was otherwise very nice and rhymed very well, it made this one mistake. Yeah. Yeah. Yeah.
Audible. I am Alana Malda and I'm from Mumbai. I just wanted to ask you that are statistical data and scientific data different from each other?
No, they shouldn't be. I mean, I hope that all data is scientific in that sense. I think data is data, right? So data is data. We can't say that this is scientific data and that is statistical data. There's only one data. And then what is different, what the data is one, the rest of it is basically what models you are, that you have in your, that you are comparing. So there's nothing like scientific data and statistical data. So when you please, those of you who want, please use that dice. It's very easy for you to collect data. Remember that you have 3 throws. That's your data. And in 3 throws, see for which of the 3 models the support is maximum. Right? You may not get a 6 and eliminate model 3. You may have to roll it several times before you get a 6. So, but you might get something else in your first 3 throws. And then remember that you have to multiply the probabilities for each of the model. And it will be a very small number, but that's called the likelihood. So that is the probability of the observed data, conditional or model 1. The data is the same. Remember, you got a 135 or a 136 or a 156 or whatever it is. That's your data when you roll the dice 3 times. You just have to multiply those probabilities, conditional or model 1, model 2, model 3, using those 3 probability distributions. And you will then find that as you collect more data, you will suddenly get a 6 and you will eliminate model 3. Then now it's only a race between model 1 and 2.